really honored that Xiaoming accepted to do the webinar. So it will be on biometric recognition in the era of AI-generated content. And as I said, it will be given by Professor Xiaoming Liu from Michigan State University. So I have a CV here, which is really impressive. For those of you who don't know Xiaoming, he's a professor at Michigan State University. He was a visiting scientist at Google Research. He received his PhD from Carnegie Mellon. And he works on computer vision, machine learning, biometrics, and he's one of the stars in our area. So he will have something very interesting to talk about today, also on a very, very hot and timely topic. So with that, over to you, Xiaoming. Please feel free to share your screen and start.
Sure. Thank you, Vito, for the introduction. So let me share my screen. Okay. So are you seeing the full screen right now?
Yes.
Okay, great. Hey, good morning, everyone. So let's get started. So today I will be talking about how do we do biometric recognition at the time when AIGC, AI generated content is so much popular. Okay, so let's get started with AR generated content. So over the past few years, AIGC has getting really attention, lots of attention from the communities, right? Because the most powerful model right now, can generating not only images, texts, audios, but even videos, right? And for example, starting with DALL-E 2 as well as Stable Diffusion, they can generate lots of realistic kind of content, as well as ChatGPT can sort of engage a human level sort of conversations between people to people. Over the years, the AIGC itself has been also progressing quite a bit with advance of different models, starting with early time we use GAN, right? Generate addressing models network trying to do image generation, starting with face generations. Later, GAN model has been extended into people develop a VAE model, and now everyone are almost using diffusion models. So those progressing of the model actually have been revolutionized how we're going to generate realistic content, including images as well as videos. And if you take a look at the current AIGC, AI kind of generate content, for example, these are some of the images from Midjourney. You can see that the visual quality of those images are getting better and better over the years, right? So, and to the point that it's getting harder and harder for computer actually to tell the difference between real versus fake content. And you can see that in the middle image, even for the human hand, which typically has been a really hard topic, a hard kind of object to generate correctly, right now, even for human hand, we can generate quite reasonable, hand appearance as well as shapes. Okay. So with that kind of development, we start to ask questions, right? For people like us working in the biometric communities, what is really the connection between AIGC versus biometrics? Right? And because we're researchers, we start with some sort of research question to begin with, right? The first question, I often ask my student is that when can AIGC can help biometric tasks, right? What kind of scenario we can consider AIGC to be helpful, to be useful for improving the biometric tasks? So here's some of the answer we have been trying to explore. For example, whenever we have a lack of domain data, for example, between training data versus testing data, we have a domain gap, right? So this is the moment probably AIGC can help us to synthesize more data. Okay, number one. Number two is that sometimes the data privacy will be a concern, especially for biometric communities. For example, we oftentimes are not comfortable of using human face images that scrap from web as a training data for the face recognition models. But right now, by using database such as WebFace 4 million, WebFace 24 million, this has been a practice. Everyone is kind of using that kind of larger scale database. So how do we address the privacy issue whenever we use that kind of database? Can we be more respectful for the privacy of the people in those database, right? So that's a kind of second scenario. And third scenario is that oftentimes when we do recognition, we need to be invariant to certain factors. So these are the parameter we want to have a disentangled system so that those parameters we can freely control those parameters. But oftentimes the real data collection you don't have this kind of disentangled data, right? So whenever that's the case, we think AIGC can also help us to do better disentanglement. Okay. So this is kind of first set question. And second set question would be that, in order to make AIGC to help biometrics itself, AIGC itself also have to be advanced, right? In other words, we want to work on advanced AIGC so that they could be more helpful for the biometric tasks. For example, right, the content generation, the control part is always very, very important, right? Because if you cannot really control the content you're generating, the usefulness of the content become weakened, right? So the more controllability you have, the better usage you have on the data you can generate, okay? So that's why we talk about we want to have more compact in controlling the content generation. And second is that we want to strive for the high diversity as well high consistency. The reason is that for biometric data, we always care about two different kind of variation. One is, inter-subject variation. Another one is intra-subject variability, right? You want both variation to be very diverse. In other words, if you generate a lots of frontal view, passport like photos, it's not so useful for training recognition systems, right? You want to generate a very diverse set of subjects, as well as within each subject, you need to generate a very diverse variations of intra-subject variations. And finally, we also want to do more disentanglement in the AIGC process so that we can actually do fine-grained control of the content. Okay, so these are the topic, these are questions I wish to sort of answer through today's talk. But before get started, I want to introduce you with one of the projects right now we are currently focused. This project is called BRILE. It stands for Biometric Recognition and Identification at Altitude and Range. So this is a project that's sponsored by ARPA. ARPA is a government organization similar to DARPA in US. They oftentimes try to sponsor, high-risk advanced research topic that could impact the future research community for the next, 10 to 20 years. So in this particular BRIGHT project, what I probably want to achieve is that if I see a people, capture at a longer distance, it could be 100 meter, 500 meter, or even, 1,000 meters, right? How can I recognize the people at a long distance? For this particular video, we're actually capturing this subject from, I think it's about 300 meters. So it's not the most challenging one, but you can see that even with 300 meters, the facial images are still, it's already getting fairly blurry. It's very, very low quality data, right? You can barely see some, appearance on the bodies, but the facial appearance gets a lot weaker. Okay, so in the past 3 years, we have been, developing different research approach, different algorithm to say that how do we handle the challenge of BRILE? Okay, can we still recognize people as far as 1,000 meters? So far, the BRILE project is the largest kind of biometric effort in US, and there are multiple university and company is involved in the project. There are 3 different phases. In phase 1, we have 9 teams. Right now, we're in phase 2. We have 5 teams. So MSU is one of the 5 teams working on this project. Okay. So over the past 3 years, when we developed the BRILE, we have been constructed a comprehensive systems. Starting with input video sequence, we do detection tracking. Then we try to recognize people from 3 different modalities, including face, gait, and body. And there's also image restoration model for face enhancement and the gait, as well as body feature extractions. Eventually, it will be a fusion between different modalities. Okay, so under this development of the BRILE project, we are developing a different approach that's leveraging AIGC. The first one I'll be talking about is trying to use AIGC to bridge the domain gap. So this was ECCV 2022 work. We also had a work trying to use AIGC to generate a training set so that we can address the privacy concerns. And the third one I'll be talking about is body matching using inverse graphics. So this is the kind of the new way we're looking at how we do the body recognition. Or you can also call this as a clothing changer person reality problem. Okay. And finally, we also use AIGC to generate the disentangled human images. So this again is for the purpose of generating synthetic data so that we can have more human images for training a model that can do a human-to-human matching process. Okay, so with that, let me start with the first one, AIGC to bridge the domain gap. So this is in collaboration between myself and Dr. Anil Jain and my student Mincho and my postdoc Feng Liu. Okay, so this is the problem set up. Suppose you have some sort of training set. For face recognition, we typically train on BGG, right? And we want to test on database such as IGBS. So between training and testing, clearly you see a domain gap. So one way to address the domain gap, of course, is trying to use synthetic modules, trying to AIGC to synthesize data, right? Hopefully this data cannot tell the difference between the synthetic data versus target domain data. So you can use a GAN kind of structure to control the process. Okay. But one innovation we are proposing this work is that we're trying to have the synthetic module and the recognition module to kind of work side by side. In other words, typically I have student A to work on synthetic modules, train the model and then give the data, right? Give the synthetic data to student B. Student B does the recognition training, does the ADA phase, ARC phase training. But here you can see that the two modules are actually working side by side, where the recognition module can send this gradient signal to the synthesized module, so the synthesized module can always synthesize data that's going to be useful for the recognition modules. In other words, the two people are actually working together, right? It's not an offline process, it's online processes, end-to-end process between just two different modules. Okay. Now, in order to do this, the precise control in the style latent space become very important, right? Because typically, when you generate this data using the encoder-decoder structure, you have this ADA in parameter, which is fairly high dimensional space. So therefore, here we feel that doing control in this high dimensional space is not easy. Why don't we try to do it in a low dimensional space? Therefore, we're learning this linear subspace which is composed of U, that's a mean of the space, as was mu. Mu is the mean of the space. U is a basis function of the space. It's like PC like sort of linear subspace, right? So with this learned space, now we can use a style coefficient O to control this ADA in parameter. Eventually, the ADA in parameter will be sent into a decoder to control the output of this synthetic data. You can see that the control can happen in both the magnitude, means how much blur, how much low quality from high quality to low quality data. We can control the degree of the low quality data. We can also control the different types of low quality data. You can see that the direction indicate, I'm essentially traveling along the different direction in my PC linear subspace, right? But the radiance along each one of the direction indicate, how much low quality I want to generate. So both the diversity as well as degree of low quality can be controlled. Okay, and then we have discriminator kind of sending feedback signals. And the control signal, the adversary regularization, you can imagine it's sort of adversary training, but the difference is that the traditional adversary attack is happening in the pixel space, right? Giving an image, I generate adversary signal, I can make the recognition to fail. But here you can see that we generate a adversary signal for the control, for the style coefficient O, so that this is also a much lower dimensional space to control the signal. Okay, it's only 10-dimensional space. Yeah, with that, you can have a recognition module send back signal so that we can update this delta or the update for the coefficient parameter O. So we'll keep doing this back and forth. So AIGC always going to synthesize the data that's going to be more useful for the recognition modules. And one byproduct for this work is that we also can measure the distance between two different databases. Because we have a linear subspace for every database, we can eventually use a linear subspace to say that how similar any two database is in terms of its styles, in terms of its image quality, right? In terms of the low-level noise of the data. So this similarity can be measured. For example, here we have a triangle sort of indicate what is a pairwise similarity between any two database, right? For example, for IJBS database, you can see that the most similar one is IJBB, and followed by wider face, okay, followed by CFP, which is actually consistent with image quality. If you look at IJBS, yes, IJBB and wider face is relatively closer to IJBS compared to other database. So this is useful in the sense that every year, we have database being proposed into the communities. This can help us to measure in terms of image quality how similar the new database is to the older existing databases. Okay. And in this experiment, you can see that we can show that by using this image synthesis module, we can help face recognition systems. So you can see that compare on different database, IJBS and tiny face, we are improving anywhere between 1 to 3% on face recognition accuracy. And this is based on the latest ADA face models. We can show further improvement in terms of rank 1 accuracy. Okay, so that's the first work I want to introduce. Let me move to the second one. So this is a work mostly done by Mincho in collaboration with Feng as well as Dr. Anil Jain. Okay, so before we try to talk about how to synthesize a database, let's try to see what is a characteristic of a labeled face database, right? So you can see that in the ideal database, we want to have a high consistency, high diversity, which means that for any people labeled as the same subject, I want to make sure the label is correct, right? I don't want two people being labeled as the same person. So the high consistency is on the label, how clean the label is. But the high diversity is trying to say that for multiple people of the same subject, I want those images to be as diverse as possible. In other words, I want those triangles to occupy the hyperellipsoid, as big as possible, because that means that I have sufficient diversity, right? For every people, for every subject. So that's an indication of the good database, okay? However, if I use the unconditional generation, you can see the unconditional generation, there's no ID control, right? I cannot really control, the identity of newly generated images. So therefore, I will have low consistency for this kind of unconditional generation. And I can also generating, frontal view images. So, but in that case, I have a low diversity because there's no style variation. Everyone is frontal view, okay? And finally, I can also generate images, using traditional method, such as GAN-based method. This kind of method turns out to have low uniqueness, meaning I cannot generating many unique subjects. So we'll show more experimental results later. So therefore, we want to make sure that our method of generating the database is more similar to A, but not B, C, D. Okay, so with that, we propose a two-stage approach. Stage 1 in DC phase is trying to do a sampling, essentially generate a lot of unique subject ID. Okay, so this is using unconditional DDPM to generating, just unique person, mostly in the sort of frontal view. Yeah. And then the second stage, we have a sort of the star bank, and then we choose any image from the star bank. Star bank typically indicate, people wearing having different pose, having sunglasses, having some of the special effect, right? So we call each one of them as a particular star. So with the star imager, now I can do a mixing stage, trying to take in the identity information from imager A, okay, taking the star information from imager B, and then try to mix them together, generate the final images. Okay, so final image is supposed to have the identity of A, but the star of B. Okay, but the issue here is that we don't really have ground truth data, right? In other words, I don't have the ground truth image of subject A with star B, right? So therefore, in this generative process, how do we ensure the ID consistency, right? How do we ensure the star diversity? I mean, the star need to follow B, but ID follow A. How do we make sure that's the case when we don't have, ground truth training pairs? Well, here is what we are proposing. We essentially trying to say that we want to avoid, make sure that we want to avoid the final image is the same as subject A, because then the star there's no diversity, right? We also want to avoid this because then the ID is incorrect. Okay. So eventually we're taking two images of one subject. This image actually, is the same image, and we want to make sure that let A provide the fine details of ID, but let B providing the low frequency stars. So one way to achieve this is that in B, you can see that we do this patchwise spatial computing the mean and variance, and then trying to do the polling, so generate the mean and variance. So eventually the SI do not carry any ID information because SI is computed from different patches. So we essentially break kind of the identity information by doing patchwise operations, right? Since the second imager do not have any ID information, so therefore the ID have to come from the first imager. So that's the kind of the design choice we are making. Okay, so you can see that conceptually we're basically, make sure the second image is really blurred and low quality, and then do the generation. Okay, so you can see that how when we change the stuff, how the final image is being changed by following the ID of the image A. Okay, we repeat the process, eventually generate a database. Okay, so here is some example. You can see that given the ID image, we have 4 different styles, and the second row are basically the synthetic data based on the given ID photo. And similarly, for the real photo, we can also generate, 4 different styles. And this is for the stage 1, saying that for stage 1 process, if you compare with the GAN-based approach, you can see that DDPM can generate a lot more unique subject, right? So you can see that if I generate about 10,000 people, 10,000 images, right? About 70% of those 10,000 are actually unique people for DDPM. However, for GAN, there's only less than 10% are actually unique people. Okay, the uniqueness is by using the facial recognition threshold at 0.3 as a threshold. So DDPM is better in terms of generating unique subjects. And in this process, you can see that by controlling the patch size, we also, have a trade-off between the consistency and the diversity, right? So when patch size is bigger, I have, high diversity but low consistency. Well, in other words, if I make the patch to be smaller and smaller, I go other way around. Eventually, the best trade-off is patch size equal to 5. Okay, so this again showing you the comparison between our method and the previous, such as sync phase and the DG phase. And these are the different patch size, right? From 5 to 5, 1 to 1, and 7 to 7. You can see that 5 to 5 has a good balance in terms of how much variation as well as how much ID consistency, right? For 1 by 1, you can see that there's not much variation. Everything in front of you, okay? But for 7 by 7, and try to keep the ID, same ID become more challenge, okay? So therefore, we eventually choose 5 by 5. Okay, yeah. And the performance comparison is important. In this case, the performance comparison is done by the following. First of all, we're trying to establish some baseline. Okay, the baseline means that we're using Cassia web face as a training data to train face recognition model, and this will be the average performance 94.62 on 5 different databases. Okay. In comparison, we can also use the web face, the same web face, as a training data for DC face, okay? And then synthesize a database. The database will have the same size as the real images. So the real imager was about 0.5 million, and we're also generating a database whose size is 0.5 million, right? And even in terms of ID and how many images per ID is the same. You can see that in the CASIA web face, we're using about 10K subjects, and every subject has 47 images. Well, in comparison, we're using 10K and every subject has 50 images. So they are more or less similar data, right? So under the very fair comparison, because remember, this 0.5 million synthetic data is also coming from the same real images. That's very important. In other words, the DC face are not seeing additional data. DC face seeing the same CASIA web face training data of 0.5 million. Okay, so with this kind of synthetic data, we can achieve performance on testing set about 89.56. So you can see there's still some gap to the 94.62, right? This gap, we call this as gap to real. Basically, how much relative closer we are to the target kind of performance, right? So you can see that this gap is about 5.3% compared to previous sync phase and the DG phase. We're reducing from 21 to 11 to 5.3. Okay, so this is the kind of same amount as real data. Secondly, is that what happens? What if we're generating more samples? For example, we are generating 1 million or 1.2 millions, right? Instead of 0.5 millions, we're kind of double the synthetic data. So when that's the case, you can see that we can further reduce from 5.3 to 3.6. Okay, so that is good. So with more synthetic data we're generating, right, we are actually closing the gap. Okay, so but the long-term goal for this research is still that in the future, can we further improve AIGC? Can we further improving the database generation process so that this gap can become 0 or even negative, meaning we can even having better performance compared to 94.62. That will be the ultimate goal going forward. And yeah, we also show that what if you are taking DC phase and DG phases? These are kind of two complementary, generation process with 2.4 million. Now the gap is even become 1.6. So you can, keep reducing this gap by taking more diverse data as well. Yeah. Okay. By the way, I also want to mention that in collaboration with our friends in Europe, we are also hosting a face recognition challenger by using synthetic data. A lot of work has been put into this, most done by our friends. Try to say that how can we define a few protocols by using synthetic data? How can we improving the face recognition performance, right? Either training on synthetic data by itself, or combine synthetic data with real data. Also, by using synthetic data for training, can we address some of the bias issues in face recognition process? So this has been a second kind of challenge. We've done the first challenge in 2023. Now this is the second challenge in CVPR. So there's been quite a lot of submissions in the community. So if you're interested, please consider this challenge as well. And we're also organizing a workshop during CVPR. There's a few very well-known researchers come over to give a keynote talk during CVPR. Okay, so let me move to the second topic. Now I'm going to talk about body matching, okay, by using inverse graphic. So this work is trying to say that, traditionally when people do gait recognition, right, you are mostly using the walking patterns, using the silhouette information to do the matching, okay? And there's also person RID information, right? So using static body characteristic to do the matching. And in person RID, you have short-term RID versus long-term RID problems. Okay, so what we're trying to formulate is that we want to define a more sort of generic person matching problem that is giving two whole body image of fully clothed individuals. Person matching try to determine whether the two individuals are the same, regardless of their clothing, viewpoint, body pose, as well as other confounding factors. right? So what's more challenging of this person matching compared to person reality is that over here you can see that it's not entirely all kind of walking or pedestrian sequences. Sometimes one of two images could be in action. People are moving, you know, with different body pose. So how do you do matching to say they are same person or different person? Okay. So in working on this kind of problem, we trying to say that body shape is probably the most useful information to do the matching, okay? So therefore, a lot of effort in this research was trying to say that giving a single image eye, how can I recover the body shape in both the naked body shape as well as closed body shape, closing body shape. So I have two pieces of shape. One is the naked body, another one is the shape with closing. Okay, so this is a pretty comprehensive kind of implicit model. You can see that we call this two-layer implicit model, right? The ZID is responsible for generating the shape for the naked body. That will be used for classification purposes. So classification will be entirely based on ZID. It's a latent code for representing the body shape. A Z closing is trying to represent the shape with clothing, you know, with clothing on top of the shape will be changing, right? Z texture is representing the RGB color for any point on the clothing or on the bodies. So it's responsible for appearance, basically, Z texture. So with the three input, you can see that we can generating the shape and the texture in the T pose, just like this pose. Then we use the LBS-based deformation to deform the, you know, the T pose into the body pose, into the estimated body pose, right? So that I can do rendering, generate eye head. Eye head should be the same pose as my input data. And this will be having a self-reconstruction loss. That's why I call this an inverse graphic to serving as a constraint. Yep. And there's two different stages for learning. The first stage, you have to let this two-layer implicit model know that I'm trying to estimate body shape, right? That's why we're using the synthetic data where we have golden ground truth to do the training. But stage two, we only have the real image without any golden ground truth, without any ground truth 3D shape to do the training. So that's a stage two. Yeah, so this is a very typical approach in inverse graphic based approach. You have two different stages. Stage one usually is a low quality data, meaning, you know, synthetic data, but with ground truth. But stage two is without ground truth, but high quality real data. Okay, so in comparison, you can see that we compare with previous sort of ReID-based method on different database. So the improvement is roughly between 1 to 3% compared to previous SOTA method. And we also collect a new database called CCDA, where the imager including different body pose, such as play you know, basketball, play different tennis sports. So that's more activity gets involved. This also is more challenging, as shown by the low rank performance, basically. Yeah. And for 3D reconstruction, you can see we also compare with the previous work in terms of 3D reconstruction quality. Compared to ground truth, the GT, our shape is more closer to the ground truth shape in terms of body size. You can see that, right? We are less impacted by the clothing, actually. We're trying to get to the true shape, you know, be more closer to the true shape. And we're also generating the shape for the closed version as well. And these are the kind of visualization that is giving single image. We can reconstruct two different body shape. One is naked body, another one is with clothing. And this is a reconstructed image eye head. You can see that eye head is still quite blurred, right? Because modeling texture is not easy, okay? But the texture modeling quality is very important for the self-reconstruction loss. I think this is a long way to go. There's a lot more work could be done to improving the quality of the synthetic data, so that we can improving the body shape estimation. Yeah. Okay, I think let me move down to my last work. So this is the work mostly done by phone, try to do human image synthesis. We call it controllable and a versatile human image synthesis and editing. Okay, so what's the motivation? The motivation really is that the current sort of person ID database, having a rather restricted range of identities, right? So you can see that most of the data have ID, up to a few thousand, and this 10,000 is probably the largest database we have. And compared to human face database, you can see that there's about 4 million or even 24 million. The largest one is 260 million. So they are essentially in different scales, right? So therefore, unless someone make an effort to collect a human body image database, otherwise, AIGC is the way to go to generating a lot more human image data, right? In terms of both new IDs as well as more variations for every ID, for example, both are important. Okay. Now, in order to do human body image synthesis, we try to make sure the AIGC can do better control, right? For example, ideally, I want to have some sort of model, right? So I can generating diverse identity, body pose, and clothing variation, just like the real database, okay? And then I can use this generate data for training my person matching models, okay? And now, how do we do this? Well, we get inspiration from the stable diffusion model. So this has been quite advanced. I have a lot of progress in sort of recent years. It can generate in quite a lot of high quality data. But what about fine grained control of those models? That's what we're trying to achieve. Okay. So therefore, you can see that starting with a diffusion model, stable diffusion model, we're trying to create a disentangled latent space, which including the identity, body pose, clothing, and background, right? With this disentanglement, if you send into decoder, you can generate this internal representation C, then the C can be used to control the diffusion model so that the final image can be eventually controlled by the latent space, disentangled latent space. Okay, so if this is successful, you can see that I can, giving any orange image, I can change its clothing, right? While maintain the identity, I can change the background while maintain the foreground image being the same. I can also change the identity. I can change the body pose while maintain the identity, right? So any one of the 4 parameters can be changed one by one if I can do this disentanglement. Okay, so that is the goal. We call this as the latent to latent disentanglement network. Okay, so eventually we decide to construct this so-called C+ space. The C+ space comes from 2 different parameters. One is the ZT, one is internal parameter C. So by putting them together, we find that joint representation for both of them can better represent the original images. For example, given the input data, if you use a C+ to do reconstruction, you can see that the final reconstruction image is almost the same as the input image. But if you only use a C, oftentimes one of the parameters, such as body pose, such as, this is also body pose, will be changed. Okay, so C+ is a better space to do disentanglement. That's a key knowledge. So with that, you can see that we learn separate encoder, estimate 4 different variables, and then using transformers based decoding to decode the C+ space. Yeah. And again, we are using multiple database for training, deflashing and selective re-ID database. They capture, very diverse data as well as different kind of supervision signal we can use for training purposes. Yeah, this is the identity label, and we also generate synthetic 3D pose label and a background label as well. Yeah. For clothing label, we are leveraging ChatGPT. For example, given this attribute label, we ask ChatGPT to generate different prompts. And these prompts can be sent into a clip text encoder to generate a latent vector that can serve as the clothing label, basically. Yeah. Okay, so on different database, you can see that our database, our method has, with our generate data, we can, improving previous SOTA methods such as CAL because of synthetic data. right? So given one input image, we can generate multiple editing photo and use all the photo for training purposes, basically. There's about, 5% improvements. And yeah, you can also control the target pose. So this is my target pose. Then you can take a source image or kind of manipulate the pose. Okay. You can also, you can also manipulate the, you can also swap the identity, swap the pose, and swap clothing style, and swapping the background. Okay. So this is kind of the doing interpolation between two samples. The top left is I'm changing the identity from sample 1 to sample 2. I'm changing clothing from 1 to 2. I'm changing pose from 1 to 2 and background from 1 to 2. Okay. Yeah, you can do many combination of this kind of editing whenever you have disentanglement. So disentanglement is a key here. Yeah. Okay, finally, I have 3-4 minutes. Maybe I can try to summarize some of the other research direction I think we have been working on, under the BRIDE project. One big topic right now is that how does the larger language models or language vision models helping biometrics? Okay, I think this probably deserve another talk, so I didn't bring those more recent work which we are publishing this year CVPR. One is a Big Gate in collaboration with the Sichu's group, and as well as a Clip 3D Re-ID. So Big Gate is trying to using Dino V2 to help gate recognition, and then Clip 3D Re-ID is trying to use again Clip model to helping person Re-ID models. So I think it's a trend to leveraging the language vision model to extract information from those models to help us to do the biometric recognition. Internally, we're also trying to study how does LVM can help with face recognition, because face recognition is something that we always, starting with web face 4 million database, right? Using AdaFace or ArcFace loss functions. But what if we're trying to study with language model, vision models? How can we do facial recognition, for example? Okay. So that's a big topic. Other topic including generic face recognition loss. I think AdaFace loss, many of you probably already quite familiar with, and this also is well received in the GitHub. It's become a latest kind of face recognition loss function design, AdaFace. And larger set-based face recognition, I think CA face is something actually I like quite a bit, because my first CVPR was 2003. That was video-based face recognition. And CA face is also a video-based face recognition, but I think it's much better work. It trying to answer the question that if you have 2 images, 5 images, a million image of the same person, how do you learn a single vector from those million photos? If the 1 million photo is all about the same person, right? How do you accumulate the information together from a photo collection to do recognition? So that's what CFA is trying to address. And finally, this year CVPR, we also have a KPRPE work, which trying to answer the question that is, in low quality data such as Braille, oftentimes face alignment will fail. You cannot really align the face very precisely because of low quality data. So in that case, how do you design a new VIT architecture that can make sure face recognition is still working well whenever you have misalignment? So he showed that this position encoding is not only good for face recognition, but even for gate recognition. We can benefit from this position encoding as well. So you can take a look at this KPRPE work. Okay, so here are some of the future direction I think will be important for some of the biometrics activity that many of you are interested. That is, we feel that there's a lack of research in doing open set recognition, because in real world applications, most of time in real world, we're having an open set scenario. We're not dealing with closed set, right? Because there's a little control on the subject being tested. So therefore, most of the time we're dealing with open set in real world applications. But most of the database or protocol we define in public database is all closed set. So there should be more research kind of moving to the open set recognition problems. And secondly, that how can we do fusion between face, body, and gait, right? How different modality can be fused together? Eventually, can we generate such a social security number for every people? Almost this number can integrate all the biometric signature on your body, basically. Okay. And the thirdly would be that can we push AIGC to make sure the gap to real is 0 or even negative by only using synthetic data, not involving real data. Okay, we're trying to say that how well we can essentially reconstruct the statistics from the real imager data set so that we can push to 0. Another topic will be expandable recognition systems and how do we do 3D clothing modeling for biometrics, for body biometrics. And finally, leveraging LLM for face recognition, which is very fine-grained recognition problems. Okay, so take-home message is that with the progress of AIGC, its contribution to computer vision will continue to grow, right? High accurate demand in CV, we oftentimes, very care about accuracy, right? We are also calling for advancement in AIGC, especially in controlled generation. Okay, so understanding and quantifying the equivalency between real and synthetic will be important. It will be a fundamental topic going forward. Okay, I'd like to thank my students and sponsors for sponsor our research. I can take any questions that you might have. Thanks.
Yeah, thank you very much, Xiaoming. This was a very interesting webinar, and there are questions being posted in the chat. So let's go. We have a few minutes for the Q&A, and hopefully we can address as many questions as we can. So the first one I'm reading from Johannes is on face recognition with synthetic data. And the question is there a danger that if the intra-subject variance of the synthetic data extends beyond a realistic distribution, that the trained face recognition model will be susceptible to morphing attacks? Can we avoid this? So what's your thought on that? So that's in the chat.
Okay. Yeah, I see that. It's an excellent question. So yeah. So you see, I think if you imagine the intraclass variation is a hyperellipsoid, right? We're trying to push the hyperellipsoid to be as bigger as possible. It's like a bubble, right? You want to push them as big as possible because the bigger the bubble is, the more variation you are creating. But the problem is that when the bubble is too big, as you said, right? The trustworthiness or the confidence of it's still the same people become weaker and weaker, because eventually we still have a face recognition model to tell us whether anything within the bubble is still the same people. That face recognition model is going to become more and more problematic for the samples around the boundaries, not the sample interior centered to the boundaries. So therefore, your confidence for the boundary point become weaker and weaker. So for generating those kind of weaker points, you are essentially reducing the consistency. Therefore, it will be a trade-off to say that how much you want to push and how much confidence you have in those boundary points.
Yeah.
I think that trade-off, I don't know if there's a theoretical way to do it, but right now it's mostly experimental way to do it. Okay, because the face recognition engine is not perfect. You only have like, let's say 98% accuracy. That's why we have to stop somewhere. We cannot fully generate a complete ellipsoid. That's my feeling. Yeah. In terms of morphing attacks, you are right. Yes, when you're generating, not confident point, these tend to be the, morphed images basically between neighboring subjects.
Yeah, so that's very interesting problem. So that means there's more research to it than just doing it through face recognition, right? So as you said, there's a trade-off if you do this synthetic issue. So also, Joanna, on a related topic, is asking about the potential issue of introducing bias when training recognition models with synthetic data. So is that something that you've observed, that maybe the bias gets worse, or does it get better? So maybe a comment.
I see. Good question. So I think there's a different kind of bias, right? For demographic bias, I think training on synthetic data would potentially become less because synthetic data, we can control the demographic groups, right? We can make sure they're all balanced. But there will be other kind of biasness might be introduced on synthetic data because of the domain gap between synthetic data versus real data. So it's a potential that model training on synthetic data will be biased toward to the synthetic data when it's used for testing purposes. So, but I think the hope here is that face recognition model eventually is still utilizing more low frequency information to the recognition. And the real versus synthetic biasness mostly happen in the high frequency domains. In other words, even though the model is taking synthetic data as training, but when it tests on the actually real data, it might still be okay because it's using low frequency information, which is the same between the real and versus synthetic for doing recognition purposes. So therefore, my kind of hypothesis is that right now this gap to real is not due to the biasness, is mostly due to the variation we are creating in the synthetic data is not as diverse as detailed compared to the real data. In other words, some of the real data variation are still getting lost in this AIGC process. You cannot fully copy or you cannot fully reproduce all the variations in the original real data. That's why you have this gap to real eventually on the testing.
So these tails are really, of the distributions, they are really difficult to model, I would imagine, right?
Exactly. So I think we are posing a more challenging problem for AIGC. That is, can you make sure you cover all the variations in the real data without losing anything? If the answer is yes, then I think we should see 0 in the gap to real.
Yeah. So in that respect, impact of synthetic data also, Agnes was asking if you see any impact on biometric template protection. So is that something where synthetic data makes sense? Maybe just a thought, because that's a different, right? So
yeah, I'm not expert. To be honest, I'm not really expert on biometric template protection. So I don't know if I can provide a reasonable answer to that question. So this is a little bit outside my expertise. Yeah, sorry about that. Yeah.
So there's also suggestions. So what would you see as a research direction, probably in relation to synthetic data in multimodal biometric systems? So is the research on generating multimodal synthetic data, like more than face?
Yeah, I see. I think that's a good topic because multimodal data is very little. We have very little multimodal data, right? So if one can generating, body, gait, and face data, synthesize body, face data for a larger number of subjects, that will be very, very useful for the community. But that's not easy because this almost has to do with the video generation, right? You see Sora, Sora only generating a few people walking in the Tokyo street, right? But you want to generating, thousands or millions of people with different walking styles. So that is a challenge problem, but I think that's something worthwhile to study because oftentimes I feel that working at AIGC can actually eventually help us to do recognition problems. Because in order to make AIGC generate data really realistic, you have to understand motion, you have to understand people-to-people difference. So that understanding will eventually help in recognition. So if you are sick of doing, recognition problems, switch your gear, working a little bit on the AIGC side may give you more insight for you to come back to recognition problem later on.
And also with multimodal data, right? So there's not that many data sets, especially not large scale, out there that you can use for this task. So if at some point synthetic data can fill that gap, that would already be very usful for the community.
Exactly. That's a very good topic. Yeah, that's a very good topic.
So if we go to another modality, so Rajesh is interesting in the body shape matching that you did. And the question here is how unique is body shape matching, actually. So in comparison to other modalities, right? So what does it mean in terms of different error rates and things like that? So what are your thoughts on that?
I see. So let me go to the body shape. So as you see clearly, the body shape is hard, right? We never claim that the estimated body shape, for example, the ZID, right, will be very accurate representation for the body shape because there's just no ground truth. It's only estimation. But this estimation tend to be discriminative, meaning we want it to be able to tell the difference between people to people. So my feeling that the idea is mostly 3D driven kind of representation learning. Eventually, my hope is that it will be complementary to traditional 2D based ReID method because most of the ReID based method is still based on appearance. So we are taking a different approach using 3D information. So the hope is that the final ReID model will be a combination of the 3D representation such as ZID together with traditional 2D based ReID method. That's also being shown by some of our results because we do see that even score level fusion between ours plus the traditional 2D method do help the performance. So that's a complementariness. There's still usefulness in the 3D information, even though the 3D itself is very hard to estimate.
Yeah, very interesting. So another maybe more technical or privacy related question from Gitagnali. So what is your take on identity leakage in the generated data, right? So the generators need to be trained on something. And so how do you ensure that what you generate is not sampled from the points that were used for training, right? In the some latest.
Good question. Yeah, I think one thing people should be doing in generation is that every time you generate, let's say, a million level database, for every generated image, you want to look for the closest training subject in your AIGC training data. If the distance to the closest subject is too closer, we should throw them away. In other words, any generated subject should be sufficiently away from any one of the training subjects. I think that could be implemented in our generation process.
Yeah.
If that's been done, then we are ensure some, there's no leakage basically. But leakage will happen. So this kind of step is necessary.
Yeah, so
right?
and it's also a general approach, right? Across different models, GANs, diffusion models, you can always use a similar approach to test if this was already in your training.
Exactly. In some sense, this leakage is a good thing for sort of IP protection peoples, right? For example, Adobe, when they have a photo stock, they want to use an AIGC model to generate some new trademarks, some synthetic photos. They want to trace back to see which one of the training data actually contribute the most to the synthetic data. This has been quite popular topic right now for IP protection. Yeah.
Interesting. So another question here is on the generation process, right? You talked about diversity, how GANs maybe generate less diverse images than diffusion models. But is there a way, so Chinmay is interesting, if there's a way to establish how many new IDs can be generated using a certain training database and a certain model. So is this possible, like theoretically, or do we need just to sample and test? So
I see. Good question. You may want to take a look at Dr. Vishnu Badadi from Michigan State University. He and Anil Jain has some work to study the capacity of embedding space. So I have a face recognition models, right? I want to know that given an embedding space, what's the maximum number of people I can recognize? Okay, so I think the answer may not be exactly answer your question because the problem setup is slightly different, but I think you might get some insight on how they solve that problem. This may help you to answer that question. But you are asking a good question, and I don't think there's a paper right now to answer that question directly. Yeah, but the paper from Vishnu and Anil Jain would be most closest to what you ask.
So I see this topic really generates a lot of discussion. So just to be respectful of everybody's time, I would maybe finish here with the Q&A session. We will forward the questions to you, right? If you want to answer any of those on the YouTube channel, Xiaoming. And other than that, so to everyone in attendance also asking the questions, we try to read as many as possible, diverse ones. If we skip one, I apologize for that, but we'll try to make up for that later on in let's say, writing. And let me thank you again, Xiaoming, for taking the time to do this webinar. It was really interesting. It will be a great addition to our library, and I'm pretty sure people will look at it again, so offline as well.
Thank you, Victor.
Because it's very nice work, and I see that there's material, so we could probably do more than one webinar on the research you are doing. So really strong work and really impressive results. So thank you very much for being our speaker today.
Thank you, Victor. Yeah, I enjoyed the talk. Thanks. Yeah.
Thanks. Okay, to everyone. So this closes the webinar for this time. And if you're interested to see it again, please wait for the recording, which will be online on the website of the Biometrics Council and also the YouTube channel of the Council. So take care and goodbye.
Yeah. Bye-bye, everyone. Bye.